For decades, NASA has launched telescopes into space, but the James Webb Space Telescope, JWST, is the first that can compete with its capabilities, despite its hefty price tag and protracted development time. As an observing facility, the JWST has never been looked at with such anticipation. However, the larger, more powerful telescope is already proving its value with a startling discovery concerning the warp bubble. But what exactly is a warp bubble? So, what has the JWST uncovered thus far? To be more specific, though, should you feel fear, the expanse of space contains many intriguing destinations. The universe is filled with innumerable galaxies, black holes, and other objects such as exoplanets. The human race is a curious one, always looking to expand their knowledge of the world around them. Inquiring minds want to know what lies beyond. Is it possible that some of the aliens we share the universe with are on par with us cognitively? Is there any chance that we've found an exoplanet with microbial life? However, the vastness of the universe presents a challenge to space exploration. In the grand scheme of things, Mars isn't that far away, but before landing on their new homeworld, volunteers for Elon Musk's colonization attempt will have to undergo more than 5 months of transit through the hazardous environment of deep space. However, suppose you want to use present technology to travel to Proxima b, the exoplanet closest to Earth. It's wishful thinking to believe that the distance to the exoplanet from Earth is 4.24 light-years. To put it another way, the nearest exoplanet is around 25 trillion miles away. Given that a light-year is 5.88 trillion miles, that's not going to work out at all. This, however, will not deter us from further exploration. After all, we have already found ways to reach faraway stars. Astronomical telescopes, however, even if we are unable to physically approach these objects, may allow us to learn more about them by sending powerful eyeballs in their direction. The practice of launching space telescopes by NASA dates back many decades. The Hubble is one of the most well-known space telescopes, and astronomers use it to study distant regions of the universe as it orbits the Earth. When it comes to the warp drive, though, NASA is the type of organization that can't help but keep launching satellites. Humanity now has a new tool to examine distant cosmic objects, significantly more advanced than any previous space telescope. The James Webb Telescope will take the position of the Hubble as the most powerful observatory in space. The JWST has allowed astronomers to peer farther into the past, allowing them to examine the process of star formation around the time the universe was born. It's 100 times more powerful than Hubble, allowing us to peer back in time beyond the debilitated star's 330 million-year-old view of the universe's beginnings. If you're wondering how the JWST can see billions of years into the past, it's because light from faraway stars has taken billions of light-years to reach Earth. The distant stars seen in this light from a distance of trillions of kilometers will reveal their appearance billions of years ago, although some of them may have passed away. NASA has released the first batch of photos that will be used to showcase the JWST's potential. Included are the bright regions of space known as the Carina Nebula. Several brilliant stars that are many times the size of our Sun reside in a billowing cloud of gas and dust, located about 7,600 light-years from Earth. The Stevens Quintet, a cluster of galaxies roughly 1 million light-years away, will also be visible in the photos. 4 of the 5 galaxies in this group are engaged in a complex dance, their shapes warped by the mutual attraction of their gravity. Amazing pictures of the galaxy cluster SMACS 0723 will soon be available. The light from objects behind this cluster of galaxies is warped and amplified by the cluster's own galaxies, making it a really unique phenomenon. This property allows telescopes to detect faint, faraway galaxies. In fact, this is where the JWST really excels. However, the warp bubble is unlike any other discovery the JWST will make. First, we'll define this concept of a warp bubble. Although a thorough grasp of this topic necessitates a strong understanding of mathematics, we'll make do with a simple definition for the time being. You're not technically going faster than light when you travel in a warp bubble. Rather, you're simply surfing a bubble of condensed space that is compressed in front and expanded in back. This has the effect of propelling the bubble and its contents forward at speeds greater than the speed of light. Why make such a big deal out of warp bubbles, you may ask? That's because they solve a major problem associated with traveling faster than the speed of light, which causes time to pass more slowly. Allow me to explain. Imagine you had the ability to exceed the speed of light. Everything outside of your ship would speed up, making your 3-hour visit to a tropical paradise feel like years on Earth. If you wish to obey all known physical rules and travel faster than light, you should probably end all your relationships before you go. Warp bubbles, on the other hand, don't have this problem because the space inside the bubble doesn't change. So even if you're flying at warp speed for an hour, it's still only an hour for everyone else. Warp speed is a concept well known to Star Trek fans. Since the first episode appeared in 1966, there have been 10 television series and 13 films set in the Star Trek universe, all of which contain the fantastic future technology known as warp drive. The story's protagonists travel from planet to planet in fast, powerful spaceships while exchanging messages with an alien crew. It's the torsion engine that draws people in, as the plot wouldn't hold water without it. The universe is strange, mysterious, and absurdly large. Even if you wanted to travel to the next star, the enormous distances between them would be nearly impossible to traverse. The next star we can examine is Proxima Centauri, located 4.5 light-years away. Traveling at the speed of light, getting to the star would take about 4.5 years. Any other method is slower because light travels at full cosmic speed and acts as a form of universal speed limiter. Staying close to Earth and its neighboring environment makes sense because, even with the fastest space probe developed, the long trek into the intergalactic abyss would take around 8,000 years. The Star Trek crew didn't stick close to home because they figured out how to cut down on their trip time. Therefore, they didn't bother sticking around Earth. Space and time are juggled by the torsion engine, which employs warp drive technology, and the result is thrilling. Prior to the final years of the last century, scientists had resigned themselves to the idea that a warp drive was impossible. Where do warp bubbles fit into the grand scheme of things? Let's check out Proxima Centauri, the nearest star to Earth, which is located 4.25 light-years away. That's around 25 trillion miles or 40 trillion kilometers. With a peak speed of 450,000 miles per hour, the Parker Solar Probe will be the fastest spacecraft ever built. Extremely fast, as it only takes 20 seconds to get from Los Angeles to New York City, but it will take almost 6,663 years to get you to Proxima Centauri. However, if you use warp bubbles, you can conceivably reach Alpha Centauri in 1 month, as determined by the spacecraft's onboard clock and mission control's master clock. Miguel Albirri was the physicist who, in 1994, came up with a notion that shocked the scientific community around the world. While working on his doctorate thesis on Einstein's general theory of relativity, Albirri was inspired by an episode of Next Generation, in which heavy masses can bend space and time. He immediately grabbed a scrap of paper, did the calculations, and subsequently published his findings in a scientific journal. Later that year, in his study, Albirri explains how to visualize a torsion bubble, in which space and time are compressed in front of a spacecraft and stretched back behind it, making the journey to the destination much quicker. In any case, Albirri's warp bubble has certain issues. You see, aggressively curving space with regular mass isn't enough to power a warp engine. You need exotic matter with negative gravity to reduce travel times. Albirri's warp drive would encase the spacecraft in a bubble of flat spacetime and then twist spacetime around the bubble. If a warp drive were to function, it would require either the theoretically possible form of matter known as negative mass, or a ring of negative energy density. However, as negative mass has never been seen by physicists, this leaves us with only the latter possibility. Negative energy can be generated by a warp drive by creating an imbalance between particles and antiparticles, which requires a large quantity of mass. Albirri estimated that a warp drive with a 100-meter craft would require 1.3 times 10 to the power of 23 kg of matter. It seems like you shouldn't enter this area. Fans of the warp drive have another reason to believe they will live to see a real warp drive constructed, and in the traditional way of discovering things, the way to build a working warp drive may have been discovered by accident. Warp bubbles seem like a concept that will never be realized in the real world, but a completely coincidental discovery is reigniting interest in the concept and could prove to be a breakthrough. Dr. Harold White is a researcher for the Defense Advanced Research Projects Agency, DARPA. The Eagleworks laboratory in Texas is where he and his colleagues first began publishing their findings on the potential structure of the energy stored in a Casimir cavity. The article states that White and his colleagues found a micro-nanoscale system that can anticipate the distribution of negative energy density. This appears to be the system Albirri needs to work on. Simply put, White and his co-workers were doing a microscopic experiment when they discovered something unexpected while looking into a theory proposed by Dutch physicist Hendrik Casimir regarding the dispersion of energy across wavelengths. According to White, the group's custom Casimir cavities were subjected to careful numerical analysis, which led them to the identification of a real manufacturable nanomicrostructure that is predicted to generate a negative vacuum energy density and, as a result, manifest a real nanoscale warp bubble structure, not an analog but the real thing. Albirri's concept of warp speed was theoretically possible thanks to the amount of energy produced in the experiment. White was also familiar with Albirri's plausible suggestion for a warp drive that could travel faster than the speed of light without violating generally accepted physical principles, but he also knew that the plan had been ridiculed for its reliance on unrealized theoretical materials and massive amounts of energy. White refined Albirri's initial metric and changed it into a canonical form, which drastically reduced the requirement for unconventional materials and energy. The revised idea resulted in the original theoretical design being informally renamed and is now more often known as the Albirri-White warp drive. Additionally, it provided scientists and fans of science fiction with hope that a practical warp drive could one day be built. White predicts that his or another scientist's small warp craft will be built and tested soon. However, White is quick to point out that much more research is needed before we can develop a completely functional warp drive. Yet, there is some reason to believe that one day, humanity may be able to travel the galaxy at light speed in a warp bubble, a la Star Trek. As we continue to explore the potential of warp drive and warp bubbles, we enter an exciting and uncharted territory in physics and space exploration. While the idea of traveling faster than light has fascinated scientists, engineers, and science fiction enthusiasts for decades, the reality of making such travel possible is still far from clear. However, with advances in our understanding of space-time, quantum mechanics, and the properties of exotic matter, researchers like Dr. Harold White and others are pushing the boundaries of what we once thought impossible. One of the core challenges in creating a functional warp drive is harnessing the energy required to manipulate space-time on a scale large enough to propel a spacecraft. The theory of general relativity, proposed by Albert Einstein, tells us that mass and energy can curve space-time, but it does not offer an easy path to control or alter spacetime in the way needed for faster-than-light travel. Creating a bubble of spacetime that can contract in front of a ship and expand behind it would require precise control of the gravitational forces involved, as well as an immense amount of energy to generate negative mass or negative energy, both of which are theoretical constructs and have never been observed in nature. Negative energy, as theorized by some physicists, could create a repulsive force that might allow for the manipulation of spacetime, essentially bending it in ways that would enable faster-than-light travel. However, generating enough negative energy remains one of the most significant hurdles in achieving warp drive technology. According to some theories, the Casimir effect, a phenomenon where two closely spaced conductive plates in a vacuum can produce a small attractive force due to the quantum fluctuations of the vacuum, might provide a source of negative energy. The discovery of potential structures that can create negative energy density, as seen in Dr. White's work, could offer a starting point for future experiments that may lead to the development of warp drive technology. In addition to theoretical and experimental breakthroughs, there is also the question of how such technology would be applied in real-world scenarios. Even if scientists can develop a working warp drive, it would need to be scaled up to handle the needs of interstellar travel. A spacecraft capable of traveling at faster-than-light speeds would need to withstand the extreme forces and environmental conditions encountered during such a journey. The spacecraft would need to be shielded from cosmic radiation, micrometeoroids, and the intense gravitational fields that could be encountered near massive objects like black holes. One of the most intriguing aspects of the concept of warp bubbles is the potential for it to revolutionize not only space travel but our understanding of the universe itself. If humanity were able to develop warp drive technology, it could open up new frontiers for scientific exploration. Entirely new regions of space, currently out of reach due to the vast distances between stars and galaxies, could become accessible. This could lead to unprecedented discoveries in astrophysics, such as investigating the behavior of dark matter and dark energy, exploring distant exoplanets, and even venturing into the unknown territories of other galaxies. Moreover, warp drive could also have profound implications for the future of human civilization. The ability to travel across the stars would fundamentally alter our relationship with the cosmos and with each other. It could provide humanity with a path to colonize other planets, ensuring the survival of our species in the event of a catastrophe on Earth. The ability to rapidly explore new planets and establish colonies could foster a new era of human expansion and collaboration, as well as provide opportunities for technological, cultural, and economic growth. The potential for warp drive to solve some of the most pressing challenges of space exploration, such as the vast distances between stars, could be a game-changer. If we can overcome the technical and theoretical hurdles, warp drive may one day become as essential to space travel as rocket propulsion is today. Just as the development of rocket technology in the mid-20th century allowed humanity to break free of Earth's gravitational pull and explore the solar system, warp drive could eventually open the doors to intergalactic exploration. Despite the excitement and optimism surrounding warp drive, it's important to remain grounded in the understanding that much of the work needed to make it a reality is still in its infancy. While there are promising developments and breakthroughs in theoretical physics, the road to achieving faster-than-light travel remains long and uncertain. Yet, the efforts of scientists and engineers working on these ideas continue to push the boundaries of what we know about the universe and our place in it.